Okay. Good morning, student. Today we will do the next concept in your subject VLSI, and the concept is your VLSI Design Flow. Okay. So as you can see, this is the flow diagram. Okay. Means what steps we have to follow. First step is your design specifications. Second is your design entry. Third is your compilation. Next is your functional simulation. Then synthesis. Then timing simulation. Then fitting, place and route. Last is chip implementation. Means we are going to start from the very first step, that is designing in the VLSI. And last step is chip implementation. Means we have implemented our design on a chip. In between, there are so many steps, and all the steps has the different functions. And I will explain these design steps one by one. So next is here, starting with the design specifications. Okay. In VLSI design process, it consists of several steps, and these steps are called as your design flow, which I have already discussed. So these steps are very beneficial actually to understand the overall VLSI design environment before shifting any hardware description, into any hardware description language. Means these steps should be followed before shifting into any hardware description language. We should came to know that how these steps are performed. First is your design specifications. Okay. In this step, the process starts with specification of the design. Means which is the design requirement, and these specifications act as a guide to choose the right technology. Here in this step, it means that we have to choose the right technology and to become familiar with the needs of actually vendor. Specifications actually allows to understand the entire design. So what types of specifications should be followed? First is actually a block diagram provide the detail how design chip should be fit into the entire system. These type of specifications should be kept in mind. Second, internal block diagram for every subsection, and we should have the internal block diagram of the system to which is to be designed with every subsection and its function. In the design specifications, third specifications, we should know about the timing specifications like setup time, hold time, what is the propagation delay, what will be the propagation delay, and the clock cycle time. These all specifications should be under consideration. Fourth is total power consumption. Okay, so we should know that how much power is consumed, how much total power will be consumed after designing this. Next specification should be kept in mind is total gate count. Means how many gates will be used under the design. Next specification is important, that is total cost of the target design chip. Means how much cost will be for that particular target. Then last specification should be kept in mind is package type required. Means which type of packaging we need. So these were the some of the design specifications under this step. We should kept these design specifications in our mind to develop a design on the chip. Now, the second step in the VLSI design flow is design entry. As you can see in the previous, first was design specifications and second one is your design entry. Okay. What is design entry? What is the function performed in this? Actually, in this step, we can enter a design with the schematic editor or any hardware description language. We know that yesterday I have discussed with you, there are two types of Hdl languages, that is hardware description languages. One is your VHDL and second is Verilog. So in this step, we will enter a design with the editor, with the schematic editor, or we can also enter our design with the help of VHDL or Verilog, that is hardware description language. Design entry can be further done by two methods. First is schematic entry, second is Htl entry. Means we can use the schematic editor also or any hardware description language from the VHDL or Verilog. Actually, what schematic entry done? Actually, what is schematic entry or what is the function performed by them is, actually it provides a graphical interface for design entry. That is, a design can be built with individual gates or we can combine gates to create the functional block. So gates are used in the schematic entry. Whereas in the Htl entry, we write the Htl code for the modules. Means programming part is there. So we write the Htl code for modules, their interfaces and their internal details. With the help of that, we can enter our design using the VHDL or Verilog hardware description language. Next step in the design flow is your compilation. As you can see in this flow diagram, design flow, third step is compilation. Now, in this step, once the code has been written, as in the design entry, we have entered our code using the Hdl language. So code has been written. So the next step is of compilation. Here we use the Htl compiler. It analyzes the code for the syntax errors and checks it for the compatibility with other modules on which it relies. So in this step, we will check the syntax error using the Hdl compiler, because we have already entered our code using the Hdl entry. So this function is performed by the compilation Hdl compiler in the compilation step. Now the fourth step is functional simulation. After the design entry we have done and the compilation, after these two steps, actually it is necessary to verify the circuit function of the designed circuit with expected function. Means verification process is done in the functional simulation. It actually allows the detection of functional errors in a design without having to the physically create. Means it functions properly or not according to our expected output. So errors detected during the functional simulation can be detected by the modifying the Htl code or statements. Means if we are facing the any problem in the function of that design without creating it into the physical mode, we will modify our design using the modification in the Hdl code or the statements which have already written in the design entry step. Now the next step in the VLSI design flow is synthesis. Okay. In this step, actually, it is the process of driving a list of physical components and their interconnection. Means we have to synthesize our design, because now we know that our design is functionally correct designed. So after functional simulation, next step is the synthesis process. In this process, a list of physical components and their interconnection is derived. Means which type of physical components and which will be the connection between these components is synthesized in this step. And this list of physical components is known as net list. So this net list can be used to fabricate an IC. Next, VLSI design flow is timing simulation. The timing simulation confirms that fabricated IC will operate at a specified speed. Means speed factor is always there. Because we know that each logic gate which is used in the design have some propagation delay. And due to these propagation delays, it limits the speed. It limits the speed at which the circuit is operated. So, timing simulation or the verification checks of each signal path is verified that it is not compromised by any propagation delay. Sorry. This step is actually after the synthesis process and before the circuit is to be released for the production. Like functional simulation, timing simulation is also verified for speed verification. Next is place and route. So next step is to design the circuit using available logical resources in the target chip. So in this step, we can say that this is in this step is also known as your physical design. It actually consists of two operations. First is placement of logic functions in the target chip, and target chip can be your FPGA or CPLD, where FPGA stands for field programmable gate array and CPLD is your complex programmable logic device. Firstly, we will place the component and then these components are interconnected in the chip using the function routing. So place and route means components are placed and then interconnection done between these components is the routing. So in this step, place and route, we will place the components and routing the components. Now the last step in the VLSI design flow is chip implementation. Actually, in this step, it configures the actual chip to realize the design configuration. So, means actual chip is converted into the design configuration and so that we can get a proper design on that chip, and that is performed according to the need. So this completes our first topic, that is VLSI design flow. Now the next concept after the VLSI design flow is introduction to CAD tools. As you know that CAD is your computer aided design. Okay. So we have already discussed that VLSI is actually something CAD uses the CAD tools. So actually the complexity in this various tools are there in the CAD tools. First is design entry tool, then synthesis tool, then is your functional simulation. Next is logic synthesis and optimization. Next is physical design, and then last is timing simulation. Okay, so one by one we will do these tools. As you know that the complexity and capability of VLSI technology in present is very extraordinary, but actually current design techniques are still inadequate to meet the challenges in the VLSI. So in that case, CAD tools are very essential. With the development of VLSI, that is very large scale integrated circuits. The CAD tools actually can perform a majority of time consuming and computational tasks automatically. Means we can design the design can be automatically done with the help of CAD tools. So to achieve the full potential of VLSI technology, we need to develop and use the CAD tools. And these tools actually help us to make the design process easy, fast, convenient, and accurate. So our design process taking not too much long time to develop using the CAD tools. And there are so many CAD tools. First is your design entry tool. Second is synthesis tool. Third is functional simulation. Fourth one is your logic synthesis and optimization. Fifth is physical design. And last is timing simulation. Now, we will do these tools one by one. First tool is design entry tool. In design entry tool, we can further divide it into three parts, means we can enter our design using the three methods. First is using truth table. Second is design entry using the schematic capture. Third is design entry using the hardware description language. Means one of the three can be used. Any one of the three can be used for entering a design. So actually, now what is design entry tool? This is the actually initially first stage in the design of any digital system. So this stage or this step is a manual process, or it requires designer's experience and their intuition. This step actually involves the description of the system to be designed to be entered into the CAD system. So design is entered by the three methods. First is using truth table method. Now, in this method, using the truth table method, in this method, for designing necessary hardware, truth table of a logic function or timing waveform may be specified using the components available. So CAD tool used for drawing timing diagram and transform it automatically into a network of logic gates known as waveform editor. As you know that any one of the gate can be performance of any one of the gate can be performed by the truth table or its waveform. So this method of design entry can be used only for the small number of variables. Since we know that truth table of description is possible only for few number of variables. If we are using the large number of variables, then it will be tedious. So this method of entering the design using the truth table is employed for the smaller logic functions that are the parts of actually larger circuits. Because we know that smaller circuits can be interconnected. We can interconnect the smaller circuits using the another CAD tool, that is Schematic Capture tool. So this method uses the truth table or the waveform to enter the design. Now the second method. Second method is using the schematic capture. The term actually schematic refers to the circuit diagram in which graphical symbols we use to represent any one of the circuit elements, and interconnection between these components are drawn as an lines, and the CAD tool which is used to draw such schematic diagrams is known as Graphical Editor. And this Graphical Editor actually uses the graphics capabilities of a computer. And this allows us to draw our diagram using the computer mouse. The schematic tool actually provides a collection of graphical symbols called the library. In any one of the software that works on their own library, a library which stores all the graphic symbols. So It represents all the graphical symbols for any one of the gates or the different types of gates with different inputs. So these special symbols are used and they are interconnected by the graphical way to create a logic network. This method of schematic capture of design entry is simple. But the disadvantage for this is it fails to work in the case of larger circuits or the complex circuits. The way to then design entry is Hdl. So if in larger circuits, if schematic capture fails to work, then it is better to write source code using the Hdl to enter the design. So remedy for that schematic capture disadvantage is Hdl language. So in third step, we will enter our design using the Hdl language, that is hardware description language. Now, what steps are followed in the hardware description language? Actually, in this step, we will write our code. We will write our design. We will enter our design with the help of a programming part, that is the source code. So this is the most commonly used method. Hdl method is most commonly used method for the designing of the digital systems. We know that Hdl is a computer-based language. It describes actually the hardware, because as you know, in the word, in the full form, hardware description language means it describes the hardware of a digital systems in a textual form. Actually, it describes the hardware structure and behavior, how it behaves. And there are two languages, hardware description languages can be used. First one is VHDL, that is VHSIC, very high speed integrated circuit hardware description language. And second is Verilog HDL. And both these HDLs are IEEE standard. In this method, in this design entry method, a logic circuit is, any one of the logic circuit is represented in the form of code. And this design entry method is used efficiently for designing small as well as large systems. So we can enter our code for any small or the large systems or the complex systems. So these were the three methods to enter a design in the using the CAD tools. Now, next step is synthesis tool. Next is your synthesis tool. Okay. Now I have already discussed with you that synthesis actually is the process of transforming an initial specifications into a logic circuit. So, synthesis CAD tools generate efficient implementation of the circuits for such given specifications. And the output of synthesis tool is a set of logical equations that describes the logic functions. These actually logic functions or the equations that are generated on the basis of designer's input to the CAD tools are not optimal for in the optimal form. So some of the optimized techniques are used to obtain the logical equations which are not functionally correct, but it is optimized for the design goal also. So this is the function of the synthesis tool. Now the next is your functional simulation. After the design entry and initial synthesis, it is necessary to verify the function of design circuit with our expected function. Means our circuit is performed according to our expectation or not. The CAD tool which is used for this purpose is functional simulator. It actually simulates the circuit function from its logical equation, because we know that our design has been converted into the logical equations by using the synthesis tool. So functional simulator actually simulates the circuit function from its logical equation and the outputs of the simulator are obtained in the form of actually truth table form. Truth table form, or you can say also using the timing diagram also. From the truth table or the timing diagram, we can verify our design circuit operates according to our requirement or not. If our simulation process output of this step, or you can say output of the simulation, is not the desired output, actually we are not getting, so the process should be repeat unless it function properly, so that correct design is obtained in the last. So this is the function of this step. Now the fourth step is logic synthesis and optimization. Now we know that our circuit is functionally correct to design. Then after this step, design is obtained using the logic synthesis and optimization CAD tools. This is used to obtain actually optimized design, so that to achieve our design goals such as cost, speed, technology. In this process, we should take care of all these design goals. Now, the fifth one is physical design. After the logic expressions are optimized, so this is the next step for the circuit to be designed on the target chip. This step is known as physical design or layout synthesis. This step also performs two functions. First is placement of the components on the CPLD or FPGA target chip, and second one is routing, that is the interconnecting the components in the chip. For this step, we have to use the placement and routing CAD tools for this purpose, that is for this physical design process. Now, the last is timing simulation. In this case, we know that functional simulation process assumes to be with a negligible propagation delay time of the logic gates. Means we are not considering the propagation delays in the case of functional simulation, and it is assumed to be as negligible for the logic gates, but this is not true in the case of your practical circuits. So there is always some time needed for signals to propagate through the logic gates. Means some time is needed so that our signals has to be propagated through the logic gates. So in this step, it is necessary to take care of propagation delays while designing the digital circuits. For this purpose, we have to use the timing simulation process. Actually, what it does, that is, it simulates the actual propagation delays in the technology chosen for the implementation of the design. And the CAD tools used for this purpose is timing simulator. CAD tools used to evaluate the expected delay of the design circuit so that we can verify the speed of our circuit. So these were some of the CAD tools used in VLSI. Okay, now students, the next topic is Eda tools for design. Firstly, we should know that what is EDA? What is the full form for the EDA? That is Electronic Design Automation Tools. Means electronic circuits are designed automatically using these tools. As we know that in earlier years of IC design, the chips were built by manually. But rapid growth in the speed and complexity of the IC integrated circuit design, we have to use a powerful set of electronic design automation tools. And these tools actually are used by different tool vendors for different design processes, such as design entry tools, simulation tools, synthesis tools, and implementation tools. So various type of design entry tools are available, simulation tools, synthesis tools, and last is implementation tool. Now, what are the various design entry tools? First is Xilinx ISC suite. Second is Ultramax Plus 2. Then third is Mentor Graphics HDL Designer. And next is Ultras Quarters. Out of four, in our lab work, we will use the Xilinx ISC suite for designing entering of our design. So these all are the four design entry tools. Next is your simulation tools. The various simulation tools is Synopsys VSS, that is high performance VHDL simulation. Then Model Sim, that is model technology. Then Cadence NC tools, that is based upon VHDL or Verilog language. Next is quick turn design system tools. These all are the simulation tools. In this, we can use any one of these for simulation process. Next is synthesis tools. In synthesis tools, we have again four synthesis tools. Out of them, Xilinx synthesis technology tool is used for synthesis in our lab work. So first one is Xilinx synthesis technology. Second is Cypress synthesis. Third is Synopsys FPGA Express and FPGA compiler. Last is Trice and Fast chip. Out of four, we will use the first in our lab work. Now the last is implementation tool. In implementation tool, we have again four type of implementation tools are available. First is Ultramax Plus IE. Then is Active Designer tool. Then Quick Logic Quick Pro. And last is Xilinx Foundation series. In this again, we are using the Xilinx Foundation series during the lab. So these were some of the EDA tools for design, EDA tools used for design. Now the next concept is hardware description languages in detail. Okay. So HDL stands for hardware description languages. This is actually a computer aided design tool for the modern design and synthesis of your digital system. As we know that integrated circuit technology advances. So in that case, digital systems become more complex and more complex. And due to their complexity of the design system, such systems are usually retained using high density programmable chips or required sophisticated CAD tools. So HDL is an integral part of such tools. I have already told you that HDL is the integral part of such tools, because we have to we have to enter our design using the HDL language. So this is the integral part of that type of such CAD tools. And it's very efficient tool for implementing and synthesizing the design on the chip. Also, this language is a computer-based language, means that it describes the hardware of any digital system in the textual form. Also, it describes its structures, its behaviors, and there are two types of hardware description languages. First is VHDL and second is Verilog. And these both languages are IEEE standard. And these both are very popular among the industries. Now, the next is, what are the various HTL capabilities? We will discuss it one by one. Now, first capability of this language is it uses an exchange medium between the chip vendors and the CAD tool users. As we know that HDL entry can be done, design entry can be done using the VHD or Verilog. So always a battle between a VHD and Verilog, that which one is best. VHDL actually is based upon Pascal style syntax and Verilog is based upon your C language. Actually, VHDL follows the Pascal style syntax and Verilog, that is based upon C. So these are the some of the capabilities why HDL increases the productivity because of its capabilities. So CAD tools users describe the actually behavior of the design at higher level for simulation by using the proficiency of your HDL language. Now the second capability of HDL language is it results in the reduced design cycle time. So faster time to market and it reduces the overall cost. Now the third is HDLs are used to write executable specifications for a piece of hardware and combining these pieces of hardware resulting a component. And if we further joining all the or integrating all the components, it will describe a circuit or a system. That so it means this language supports the hierarchy. Now the fourth. This language includes various elements like components, packages, objects, data types, functions, procedures. And these elements help us to make integration of large design easier. Now the next capability is any type of description such as algorithms, Boolean expression, or FSM, that is finite state machine, can be modeled by using this language. Now the next capability is this language is content programming language. Means this language has ability to model multiple parallel processes like flip-flops, adders that automatically execute independently of one of the another. And if there is any change to the process input, automatically trigger the update in the output, in the simulator's output. Now the next, we can model our circuit using the three different modeling style. First is data flow, second is behavior, and third is structure. Means any circuit can be modeled by, any system can be modeled by one of the three different modeling style, that is data flow, behavior, and structure. So this language support all these three modeling styles. Next is this language provides the design portability, means design circuit technologies changes rapidly, so its design is portable. Due to the reason behind that is this language is IEEE and ANSI standard language. So the models which are designed using this language is always portable. So this language is IEEE and ANSI standard. Next is this language is used for describing the digital systems, and such type of descriptions can be used by using the simulator without having to actually construct the system, because we know that we have the timing simulation also, function simulation also. Now the last capability of this language is test benches can be written using the same language to test other VHDL model. Means we can check the other VHDL model using or writing the test benches using this language. So electronics and computer engineering students always should be familiarized with this language. So these were the some of the HDL capabilities. Now we will do the next concept, that is Hdl advantages. There are so many Hdl advantages. First is HDLs are used in order to speed up the design cycle time. Second is we can reuse already designed units using this language. Third is the designs which are made by using this language are always portable, so that we can port our design from one vendor platform to the another. Next is the design based on HDLR technology independent also. This language also allows the fast exploration of design alternatives. Means we can design our circuit using so many methods. This language also allows automation in the synthesis process. Next advantage is it has shorter design time and reduced time to the market because everything is automatic. This language provides concise representation of circuits by using the different statements like data flow statements or the behavior statements. Next advantage is it allows easier design verification. And the last one is flexibility increased in using these languages means we can change our design. So this language is very flexible. So these were the some of the HDL advantages. Today we have completed our lecture. So we will meet in the next lecture with the topic comparison between VHDL and Verilog. Okay, thank you.